inovasi ahli muda pengukuran jalan. Prodi Teknik Sipil memiliki ruang sekretariat Prodi Teknik Sipil serta ruang dosen Prodi Teknik Sipil. Pengabdian kepada masyarakat, himpunan mahasiswa sipil juga berperan aktif dalam membangun infrastruktur di Desa Logisadeng Bogor bersama Ikasila. Beberapa seminar di program studi teknik sipil diantaranya Seminar Konstruksi Indonesia di JI Expo Jakarta tahun 2018, penyuluhan rumah aman bencana oleh para dosen prodi teknik sipil yang diselenggarakan oleh BPBD DKI Jakarta. Sejumlah prestasi kemahasiswaan program studi teknik sipil, antara lain juara 1 Lomba Tingkat Nasional Earthquakes Resistant Building Design Competition di Universitas Pelita Harapan tahun 2018. 7 besar nasional Lomba Kompetensi Jembatan Indonesia KJI kategori Jembatan Baja yang diselenggarakan oleh SEMRESTEK Dikti di Makassar tahun 2019. Program studi teknik mesin. Program studi ini memiliki fasilitas 7 laboratorium, yaitu Laboratorium Perancangan dan Bedah Produk sebagai tempat uji kompetensi lembaga sertifikasi profesi dengan skema perancangan mekanik umum yang terdapat di ruang teknobis, Laboratorium CNC, Laboratorium Prestasi Mesin, Laboratorium Metalurgi Fisik, Laboratorium Mekatronika, Laboratorium Fenomena Dasar Mesin, Laboratorium Energi Baru Terbarukan EduTechnopark, menggunakan sistem biodigester dan pyolisis, serta sistem pemanfaatan air wudhu untuk menyiram taman dan tanaman kearifan nasional. Program studi teknik mesin memiliki ruang sekretariat prodi teknik mesin serta ruang dosen prodi teknik mesin. Inilah beberapa prestasi kemahasiswaan Fakultas Teknik Mesin, antara lain meraih silver medal dan gold medal pada kompetisi Regional Education and Student Product Exhibition SEMRESTEK periode 2018 hingga 2019 di Port Dickson Politeknik Malaysia. Meraih gold medal pada International Competition Students Creativity of Technology and Culture ICOSTATEC 2019 Jakarta, serta meraih juara 2 di ajang Lomba Inovasi Sumber Energi tingkat nasional IEIC Indonesian Energy Innovation Challenge 2019 di Makassar. Program studi teknik informatika. Program studi ini memiliki fasilitas 4 laboratorium, yaitu Laboratorium Network and Security, juga sebagai tempat uji kompetensi Network Designer, Laboratorium Penelitian, Laboratorium Artificial Intelligence dan Komputasi, Laboratorium Software Engineering, dan tempat uji kompetensi Lembaga Sertifikasi Profesi Software Engineer. Prodi Teknik Informatika memiliki ruang sekretariat Prodi Teknik Informatika serta ruang dosen Prodi Teknik Informatika. Inilah beberapa pengabdian kepada masyarakat program studi teknik informatika, antara lain Internet Sehat untuk Ibu Kader Posyandu Budi Harapan Depok tahun 2017, workshop Sistem Keuangan Desa di Kecamatan Babakan Kabupaten Cirebon untuk meningkatkan akuntabilitas laporan keuangan desa Juli 2018. Peningkatan pangsa pasar untuk UMKM Batik Cirebon tahun 2018. Edukasi digital marketing Pondok Petir Depok tahun 2020. Pengabdian kepada masyarakat mengenai rainwater harvesting system untuk mendukung pengembangan potensi Pulau Pramuka Juli 2017. Serangkaian beberapa kegiatan mahasiswa Prodi Teknik Informatika mengikuti pameran produk IT dan panitia lomba robot tahun 2018, studi kunjungan ke bisnis startup pada tahun 2018 dan 2019, serta teknik Pancasila bangun desa ke berbagai daerah di Indonesia. Prestasi mahasiswa Prodi Teknik Informatika, finalis tingkat nasional pada Techno Corner 2020 Internet of Things Development Competition di UGM Jogja, Maret 2020. Meraih gold medal dan juara 2 pada International Competition Student Creativity in Technology and Culture ICOSTATEC 2019 di Universitas Pancasila pada tahun 2019. Program studi Teknik Industri. Program studi ini memiliki fasilitas 4 laboratorium, yaitu Laboratorium Statistik dan Optimasi, Laboratorium Manajemen Industri dan Teknik Industri, Laboratorium Sistem Produksi, Laboratorium Perancangan Sistem Kerja, dan Ergonomi. Program studi Teknik Industri memiliki ruang sekretariat Prodi Teknik Industri serta ruang dosen Prodi Teknik Industri. Prestasi kemahasiswaan program studi teknik industri antara lain juara 2 Entrepreneur Day Universitas Pancasila 2018 yang diselenggarakan oleh CEDC Universitas Pancasila. Kegiatan kemahasiswaan prodi teknik industri di antaranya IESC, kontes keilmuan teknik industri, pelatihan software pro model, AutoCAD, Microsoft Office, Industrial Mini Project, IMP, mengembangkan kreativitas mahasiswa dalam memodifikasi barang bekas menjadi barang yang memiliki nilai guna. Program studi teknik elektro. Program studi ini memiliki fasilitas 9 laboratorium, yaitu Laboratorium Fisika, Laboratorium Telekomunikasi, Laboratorium Sistem Kendali, Laboratorium Digital, Laboratorium Elektronika, Laboratorium Pengukuran Listrik dan Instrumentasi, Laboratorium Komputer, Laboratorium Penelitian, Laboratorium Cisco, tempat uji kompetensi lembaga sertifikasi profesi, skema fiber optik dan program logic control. Ruang fungsional lain seperti ruang dosen, ruang rapat elektro, ruang administrasi pelayanan fakultas dan elektro, ruang diskusi dan baca elektro, ruang sekretariat Forte Regional 3, ruang kelas kuliah dengan kapasitas 30 hingga 70 mahasiswa. Inilah karya tugas akhir dan ruang karya ilmiah program studi teknik elektro. Program studi teknik elektro juga pernah mengikuti serangkaian kegiatan seperti lomba robotik, menggelar seminar dan ruang kuliah umum. Sebagai bentuk pengabdian kepada masyarakat, berpartisipasi aktif dengan melakukan penyuluhan instalasi listrik rumah tangga yang aman dan aktif dalam membangun infrastruktur di Desa Lumisadeng, Bogor. Fakultas Teknik Universitas Pancasila di level internasional menggelar Innovation Research for Science, Technology, and Culture (IRSTC 2019). Selain itu, Fakultas Teknik Universitas Pancasila juga memiliki satu program studi magister teknik mesin. Program studi yang terletak di Jalan Borobudur, Menteng, Jakarta Pusat ini memiliki beberapa ruangan fungsional, di antaranya ruang sidang MT, ruang kuliah, dan beberapa ruang lab komputer. Fakultas Teknik terdapat beberapa ruang tata keorganisasian, ruang dekan, ruang wakil dekan 1, ruang wakil dekan 2, ruang wakil dekan 3. Fakultas Teknik juga memiliki beberapa ruang fungsional lain, di antaranya adalah ruang rapat fakultas, ruang administrasi umum dan keuangan, ruang akademik, ruang satuan jaminan mutu, ruang pusat pengolahan data, ruang humas dan kemahasiswaan, ruang lembaga penelitian dan pengabdian kepada masyarakat, ruang puspek. Fakultas Teknik memiliki 7 pusat kajian serta didukung oleh kantor internasional. Ruang perpustakaan fakultas yang luas dan nyaman, tersedianya buku, baik dalam bentuk textbook maupun digital e-book. Juga terdapat ruang kecil sebagai ruang diskusi, fasilitas aula yang berfungsi sebagai ruang kuliah umum atau seminar-seminar, kelas multimedia dengan kapasitas 60 orang, didesain dengan sentuhan bergaya teater, dilengkapi fasilitas studio audio visual dan sarana multimedia penunjang lainnya. Selain itu, terdapat beberapa keunggulan fasilitas umum yang dimiliki oleh Universitas Pancasila, yaitu gedung rektorat, ruang perpustakaan umum, ruang pusat pengembangan kewirausahaan dan layanan karir mahasiswa, gedung pusat lembaga bahasa, gedung serbaguna, masjid yang bersih dan luas, bekerjasama dengan Bank Mandiri dan Bank BNI, serta layanan ajudan tunai mandiri. Pusat kegiatan mahasiswa Universitas Pancasila yang terdiri dari 23 UKM, sarana seni dan olahraga, apotik, klinik, kantin, dan koperasi. Universitas Pancasila terus memegang teguh komitmen Tridharma dengan memberikan pelayanan kepada masyarakat, pemerintah, dan industri dalam upaya peningkatan daya saing dan kesejahteraan masyarakat di era digitalisasi.
Okay, let's start our webinar. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Shalom, Om Swastiastu, Namo Buddhaya, Salam Kebajikan. Our respectable speakers, Professor Arno Smets and Insinyur Latif Gau, our respectable Dean of Engineering Faculty of Universitas Pancasila, Dr. Insinyur Budi Mulyawan Suyitno, IPM, ladies and gentlemen, attendees of the international webinar and invited guests. Let us all give our praise and gratitude to God for our attendance on international webinar Green Innovation, Green Technology Innovation, and the opening of Seminar Rekayasa Teknologi 2020. I'm Nur Suryaningsi, will be the host of the opening ceremony in this afternoon. For a brief moment, we would like to invite you to sing Indonesian National Anthem, Indonesia Raya.
Indonesia kebangsaanku, bangsa dan tanah air. Marilah kita bersatu, Indonesia bersatu. Hiduplah tanahku, hiduplah negeriku, bangsaku, rakyatku semuanya. Bangunlah jiwanya, bangunlah badannya untuk Indonesia Raya. Indonesia Raya, merdeka, tanahku, negeriku yang kucinta. Indonesia merdeka, hiduplah Indonesia Raya. Indonesia merdeka, merdeka, tanahku, negeriku yang kucinta. Indonesia merdeka, merdeka, hiduplah Indonesia Raya.
Thank you. Opening speech from the Dean of the Engineering Faculty of Universitas Pancasila, as well as the openings of Seminar Rekayasa Teknologi 2020. Please welcome Dr. Insinyur Budi Mulyawan Suyitno, IPM.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Salam sejahtera. Salam, Om Swastiastu, Namo Buddhaya, Salam Kebajikan. Good morning. First of all, let us praise and thank the presence of Allah Almighty for the abundance of grace and the joy of all of us can still gather in this place without any barriers at all and in a good health. On this occasion, allow me standing here to deliver a couple of opening sentence speeches. The honorable keynote speakers, Professor Arno Smets, as a keynote speaker at the 4th International Webinar Series. He is a professor in solar energy research, photovoltaic materials and devices group at the Faculty of Electrical Engineering, Mathematics and Computer Science, Delft University of Technology, Netherlands. Mr. Abdul Latif Gau. He is our alumni from 1998. He has more than 30 years of work experience in mechanical engineering in multinational companies, Philips Electronics, Denso Automotive, Heroes Electric ICT, and renewable energy businesses are companies that need his creative ideas in developing their business units, starting from product design and development, global marketing, and business development. Currently, he is the managing director of Tidal Energy. The Honorable Vice Dean of Engineering Faculty, Universitas Pancasila, the Honorable Head and Secretary of Study Program Mechanical Engineering, Electrical Engineering, Informatics Technologies, Industrial Engineering, Civil Engineering, and Architecture. The Honorable Delegation of BCA Bank from Corporate Social Responsibility, PT Bank Sentral Asia, CSR BCA. The Honorable of International Webinar Series and Seminar Rekayasa Teknologi attendance. Today, on November 25th, 2020, we will carry out the 4th International Webinar Series with the theme of Green Technology Innovation. This webinar is part of the previous webinar, where the webinar series 4 was conducted by the Department of Mechanical Engineering, the Engineering Faculty of University Pancasila. This webinar event will be followed by a seminar Rekayasa Teknologi, or SEMRESTEK 2020, which will be held tomorrow. SEMRESTEK 2020 is the 3rd Technology Engineering Conference, which is being held online at this time. For the seminar Rekayasa Teknologi, SEMRESTEK, this is a series of national conference established by Mechanical Engineering Department since 2018. SEMRESTEK 1, 2018, held on August 15, with the theme of pengembangan energi baru terbarukan dan green technology untuk kemandirian bangsa, the development of renewable energy and green technology for national self-sufficient energy. SEMRESTEK 2, 2019, held on November 11th until 13, 2019, with the theme of penelitian inovasi tentang sains, teknologi, dan budaya untuk mendukung tujuan industri 4.0 dan pembangunan berkelanjutan. The conference was adjoined with international conference, the 5th IRSTC, Innovation Research for Science, Technology, and Culture, which was attended by participants from some countries, including Malaysia, Korea, Germany, and others. In 2020, the Department of Mechanical Engineering, Engineering Faculty, University of Pancasila, will carry out the 3rd Seminar Rekayasa Teknologi, which will be held on November 26, 2020. The SEMRESTEK is conducted in an online webinar due to the COVID-19 pandemic. There are 30 authors who have registered their manuscripts, and the participants came from some institutions. I want to say welcome for participants of SEMRESTEK 2020. I want to appreciate for your participation in this conference. I hope your technology ideas can also participate in the development of green campus technology for the advancement of Indonesia. I, as Dean of Engineering Faculty, University Pancasila, and representing University Pancasila as well, would like to thank to CSR BCA, who's sponsoring this conference. I hope the relationship between University Pancasila and BCA will establish a closer cooperation in the future. I also would like to thank to SEMRESTEK and webinar committee for hard working with high dedication in realizing the SEMRESTEK as well as a webinar. So that's all from me. I wish this webinar was productive and beneficial for all of you. And thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Mr. Budi Mulyawan Suyitno. And in the next event, let us listen to the presentation from the speakers. We will hand it over the event to the webinar moderator, Dr. Dedelia Zariatin, STMT. Dr. Dedelia, please.
Thank you.
You're welcome.
Okay, thank you very much for this respectable webinar series and also the opening of SEMRESTEK 2020. Here we have two keynote speakers. May I introduce Prof. Arnold Smith. He is a professor in solar engineering, especially in photovoltaics, material and devices. He is a member of electrical engineering, mathematics and computer science, Delft University of Technology. And we also here have Pak Latif Gau, as the Dean already introduced this, that he is one of our alumni of mechanical engineering of Universitas Pancasila. He is the managing director of several companies. One of his Tidal Bridge Energy. Okay, maybe I would like not to waste much more time from Prof. Arnold, because I heard that he has a tight schedule. So for the first presentation, let me hand the audience to Prof. Arnold. Please, the time is yours.
Thank you, Dedelia. Can everyone see my screen?
Yes, your screen is wide open here.
Okay, then So now my presentation for. So thank you, Dedelia, for the nice introduction. Also, thanks to the organizers for inviting me to give a presentation on the research and topics which are always on my mind, and that is usually related with the energy transition, and my expertise is solar energy. So in this presentation, I would like to give first a general introduction. What are the challenges in my view? And then I will give a short introduction into how photovoltaics, so converting solar light into electricity, will, in my view, play an important role in the energy transition, but also providing energy access to a lot of people around the world. And then I focus on one technology and a collaboration I have at Delft University. That's the company Hyatt Solar, where we look into a specific technology, and that's thin film silicon photovoltaics. Also for Indonesia, an important technology, because as I will present, there are some activities and plans to build a manufacturing plant in Indonesia based on this technology. As a start, here you can see, I have to remove, wait a minute, so here you can see, and I have a pointer, sorry. So here you see the typical research I'm doing. I'm working on materials for photovoltaics, next generation, like flexible PV modules, up to crazy ideas in which we push the materials to the limit and convert solar energy also directly in chemical fuels like hydrogen, but you can also think about carbon dioxide reduction into an alcohol again as a fuel, and also a future large-scale energy system. So it's a broad range of topics. And next to that, I've developed on campus, but also online, an education portfolio related to solar energy technology, solar energy engineering. And here you see massive open online courses, which we provide to the edX platform, where we already reach out over more than 500,000 students around the world. So talking about energy and the energy transition, it's already 5 years ago that almost 200 countries in the Paris Agreement agreed on introducing policies and a strategy to try to reduce the climate change in terms of increasing global temperatures to 2 degrees Celsius in reference to pre-industrial times. And it would be very nice if we could limit this to 1.5 degrees Celsius. So these are the policies in place. And usually when I have to explain climate change to students, I make a very simplification on what is the challenge. The challenge is like handling solar energy, because if you look at planet Earth, all processes on the surface of planet Earth, the energy source for that is the source of the energy source, the sun, the sunlight. And if you look at the temperature of planet Earth, so we get an amount of energy in power, which is the solar light, but also the planet Earth as an object which has a certain temperature is emitting in the very far infrared electromagnetic radiation out into space. And this is no problem if the amount of energy coming in is equal to the amount of energy going out. So then basically the thermal budget of planet Earth is neutral. However, due our addiction to energy and using fossil fuels as energy source, we are emitting greenhouse gases. So CO2 is the dominant of one of that. And that is putting a blanket around planet Earth in which the cooling down mechanism, being the emission of this infrared electromagnetic radiation into space, is hindered. And basically what we see is that we have a little bit more energy coming in than is going out. And this additional energy is stored as a thermal energy. It's it's already a technological challenge to measure basically what is coming in and going out. You have, for instance, the NASA, the Cirrus project, where they try to do this with satellites in space. And the estimate currently is that there is a small energy difference of 0.6 watts per square meter. So that sounds to be a very small fraction. But if you do the simple calculation on the back on the envelope, and let's say we would push this excess of energy into the column of air into the atmosphere per square meters, it means that you can heat up the atmosphere with almost 2 degrees Celsius in one single year. This is not happening. And why is it not happening? Because on planet Earth, we have the oceans. These are a heat sink and they consume a lot of this additional thermal energy, which is left behind on planet Earth at the moment. And thanks to the heat sink of the oceans, we don't experience the temperature increases in the atmosphere as if compared to the 0.6 watts per square meters. So this is due to the greenhouse emissions of gases. And here you see our global CO2 emissions related to only energy. So here we emit around a little bit more than 30 gigatons of CO2 into the atmosphere. A lot of that is consumed by the oceans. Again, a lot of that by vegetation or algae in the oceans. And a small fraction of that is building up in the atmosphere. So the CO2 concentrations are increasing. And still we are increasing. 5 years after the Paris Agreement, the CO2 emissions are still increasing. This year it's expected due to the limited economic activities due to the pandemic, that this will be decreasing with maybe 10–15%. But that's, of course, is not a structural increase. And if you look at the International Panel of Climate Change, to keep, for instance, us at a scenario in which we allow ourselves to have the average global temperature only increasing with 1.5 degrees Celsius in reference to pre-industrial times, you see that our CO2 emissions have to go down very quickly to zero. And even many scientists believe that the measures as agreed on in the Paris Agreement will not be sufficient to meet this target. And also that at the second half of this century, we have to use even negative carbon CO2 emissions. So it means that we have to capture and store CO2 as well to meet these effects. So that's one challenge. The other challenge is, of course, access to energy is related to the living standard and also to the economic activities you can facilitate. And here you see, here I express it in energy available per capita per day in terms of kilowatt hour per day. That basically shows what activity you can have and what kind of society you can establish. I'm not saying that an industrial or a modern society are very sustainable societies, because there we're also using a lot of energy. But talking in economic terms, it's very important how much access you have to electricity. And unfortunately, if we look worldwide, the access to energy and access to electricity is not equal distributed. So we also have to move to an energy system in which we have a fair distribution of our energy sources. And in my view, solar energy is playing a very important role in that. And to show the importance of solar energy, I first would like to show what is nature doing itself. So nature, using the photosynthetic process, is converting solar energy using carbon dioxide and water into carbohydrates. And those carbohydrates are the chemical fuel for life. It's basically the chemical fuel which also has to pass our stomach. And here you see this beautiful process in operation. And this is a capture, an animation from NASA based on satellites, and they measure how much infrared light is being absorbed by vegetation. So that shows the activity of the photosynthetic process. And what you see here, that for instance, if you look at the northern hemisphere, there it's really seasonal dependent, and around the equator you don't have this fluctuation. But now, how efficient is the whole ecosystem of planet Earth? How much sunlight can it convert into biomass? So I've done a simple back on the envelope calculation, and basically if we average out over the entire surface of planet Earth, then we arrive at a conversion efficiency of 0.05 watt per square meter. That is the amount of energy which nature, algae in the oceans and vegetation on land is converting into a chemical fuel. And on this axis I have the last 2,000 years on the horizontal axis. So first of all, if you look at the world population has been increasing very fast. And certainly from the Industrial Revolution, it basically has exploded. So if you just think in the concept like okay, we need energy, and the first primary energy source we need is food. If you already see how much chemical energy has to pass our stomach, and if you look at the natural supply chains of making vegetation or the vegetation, turning that into feedstock, animals and meat, it means that around 7 to 11% of the total photosynthetic power has to pass our stomach. So that is only in terms of food, and this is If you also add our energy consumption, which is usually 20 times more than what we need, the 2,500 kilocalories of energy which we need as humans. So here you see that basically that we have to cut down almost every plant around the world growing. We have to consume all the algae to supply our energy needs. So it shows that our energy consumption is far from sustainable. So we have to go to sustainable energy technologies. And of course, one of the challenges is that due to the growing world population, the amount of area per person which we have is also limited. If you see in 2050, the world population will be so large. And in Europe, we always define areas in terms of soccer fields. So if you worldwide, we will have per person 1.5 soccer field of land area. And if you then look for highly populated areas like the Netherlands, there we are rather poor. We only have 1/4 of a soccer field per person. And these are the challenges, because we have to grow our food on this area. We have to live here. We have to build our infrastructure here. And we have to generate our energy on this area. So these are the challenges. And if you look at the current situation, like currently we have, we use worldwide on average 65 kilowatt hours per person per day in primary energy. Which is equal to a continuously power of 20 terawatt. And let's assume that all this energy, which is not going to happen, by the way, would be generated by photovoltaic, so solar electricity. And that we would store this energy and then use it again. It would mean that we would have, and including the losses in the storage cycle of 50%, we would need an area like this covered with solar farms to supply our energy needs. Of course, there are more technologies to do that. Let's say if you would do this fully with wind energy, so offshore, we would have to cover an area like this with wind farms. So these are enormous challenges. So what we see is that we have to become more energy efficient, reducing this number, and we need an intelligent mix in different energy sources to generate energy in a renewable fashion, such that we do not emit CO2, then distribute it and store it in intelligent way, and then consume it also in intelligent way, where we focus on energy efficiency in our consumption. And here you see a little bit of philosophy. It means that if you look at green technologies for generation of energy, like solar, wind, or hydroelectricity, it shows that electricity is becoming the dominant energy carrier. So it will replace for a large part chemical fuels and the fossil fuels as we know it today. It also means that the whole energy infrastructure has to be changed. Looking at generation, which will be more decentralized, the distribution, storage will become a very important challenge, and also the technologies in consumption. So if you think in terms of mobility, it's moving to more an electrical powered mobility, or even maybe an hydrogen powered mobility in the future. But also in regions of the world where heating is important or cooling is important. So this will be technologies which are more electrified. And then I arrive at energy transition models. In the world, you have several stakeholders who develop energy transition models. So it shows that with the current technology you have, can we move to 100% renewable energy infrastructure? And you have various scenarios by, for instance, oil companies. You have scenarios developed by the International Energy Agency. You have scenarios supported by, for instance, the International Panel of Climate Change. But for me, one of the most inspiring energy scenarios is that of the Energy Watch Group, and Christian Breyer, he's a professor at the LUT University in Finland, which has done this calculation in great detail for the entire world. So every region has its own challenges in the energy transition. But in this report here, it shows that you can go successful to 100% renewable energy infrastructure, even without using CO2 capture technologies, as I mentioned earlier, with existing technology. And what you see in this transition model is that electricity is becoming the dominant energy carrier. And interesting in this model is that if you see that worldwide on average, solar electricity, so converting sunlight into electricity, photovoltaics, will become the dominant energy generator. So 69% of the energy generation will be covered by photovoltaics. 80% by wind energy, then you have some hydropower and some other technologies. So 69% is with photovoltaics. Having said that, there are several energy transition models around, and some models, the most recent models, they arrive at a large contribution of solar electricity to the total energy generation. There are also modules where the solar energy generation is limited to a penetration of 30 to 40%. And if you look into those models, why do they arrive at a much lower number? It's very interesting because it's all related to the assumptions they have. Some of the models, they just limit the area which can be used for photovoltaics. Other models, they include biomass, which means that the need for storage is much lower. And it also means that then the contribution of solar electricity will be much more. Although a biomass, the question is whether that is really a sustainable and renewable solution for the future. And the third and the most important thing is that most people are not using the current data for cost prices of solar electricity. I will show in a few slides, it has become very cheap. The International Energy Agency, and for instance, even the models used by the International Panel of Climate Change, they are using outdated data from 10, 15 years ago. So very expensive costs for solar electricity, not what has been realized today. And that's the reason why it's, they arrive at lower penetration. And here you see how in the energy transition, this is basically the cost price of the energy, levelized cost of energy. In the transition, you can keep those cost prices the same as they are now for energy. So some people say like, okay, energy transition means that energy will become more expensive. That is not the case. And here you see like all the technologies, and if you see in this scenario, you see that the total is capex, so the amount of money invested in the different components in your energy supply chain. You see that solar electricity is a very important one. You see that the storage batteries is an important technology of the future. Converting solar energy into a chemical fuel again, so like electrolyzers is a small part. And here, certain regions of the world, also heat pumps, either for heating or for cooling, will be an important technology in our energy infrastructure. So as solar is so important, I will, and of course it's my field of interest, I will focus on solar electricity, because it means that if you look at 69% of our energy, if that should be generated by photovoltaics, we need to have a very reliable technology, which has very high conversion efficiencies per area, so very high yields. We should be able to apply it on every surface. We should have it very cheap. We should make it of materials which are abundantly available and also equally distributed around the world. It should be reliable. The lifetimes of the technology should be very long, but also we should think about the storage at the end. And Latif Gau will also talk about that in a demonstrator system in Indonesia after this presentation. But we also have to think big, because if the significant part of energy should be generated by solar electricity, are we as humans capable of thinking big? As an example, when I started my PhD working on solar electricity, that was in 1998, and this is the World Energy Outlook report of the International Energy Agency. And so they basically predicted that 20 years from 1998, we would have 2.1 gigawatt peak installed. That was the total capacity worldwide in solar photovoltaics installed. So they were claiming that in 20 years, we would be reaching this. This is what has been realized. So it's a factor 250 more than what the International Energy Agency predicted 20 years ago. This basically demonstrates that we as humans are not doing a very good job in predicting the development of technologies, and also we have problems in being visionary in what can be achieved with technology. And what you see over here, you see an exponential growth. The yellow one is the cumulative installed power, and the red is the annual market. So that is the annual total capacity added worldwide. And you see that that is around 25 to 20% of the cumulative installed. So you see the PV still demonstrates an exponential growth. And this is very important. If you look at, for instance, different energy generation technology, here I have the timeline, and this is our energy demand as it is growing due to the growth of world population and the average living standard worldwide. Here, for instance, hydroelectricity. With the introduction of the Francis turbines, we were able to efficiently convert the potential energy of water over height difference using dams into electricity. And here you see how the total installed power, and I call here effective power, that means that is the real power being delivered, how that has been evolving during the last century. And here you see, for instance, nuclear energy. And what you see here, the vertical axis is a logarithmic scale, is that you see generation technology increasing first in an exponential phase, and then at a certain point they go into a linear phase, and then the technology saturates. If you now look, for instance, to the biggest two new renewable energy generation technologies like wind energy, the wind turbines, and photovoltaics, you see that there we are in an exponential growth phase as well. The question now is, how long should this exponential growth rate continue to, for instance, reach the targets as I mentioned? Let's say if 69% of the PV, of the energy should be generated by photovoltaics, it means that we have to reach to these levels as here, and this is for wind energy. So this is the objective of the Christian Breyer scenario. If we then look at how long should this exponential growth phase continue, it means that the next 13 years we should be increasing our annual markets worldwide with 20 to 30% every year. So this growth should be facilitated for the next 13, 15 years. If I look at the predictions, and that is mainly related to the amount of investments in these technologies, This is the worst case scenario. If we don't invest a sufficient amount of money in these technologies, we might end up at these levels. So there's way beyond any level where we should be. So it's very important for the financial sector, but also for governments to invest in the coming 10 years to facilitate the market such that you can achieve the real generation power you need for a 100% renewable future. This exponential growth, which we have seen the last 20 years, is an enormous success, and it's related to the enormous reductions in cost prices. So here you see the module cost price versus the total installed capacity worldwide in terms of power. And what you see here that over a period of the last 40 years, the cost price of modules have been decreased with a factor of 250 degrees. And this is what we call learning curves. And the interesting thing is that we as human beings, we have always trouble in thinking in double logarithmic plots, because we always underestimate how fast a technology can become cheaper and competitive. And this is one of the reasons why the International Energy Agency is underestimating the important role of solar electricity in the future. Of course, this is only modules, and if you look at a total system, you have more components, inverters. If it is a standalone, you also have batteries, and Latif will also talk about this in the follow-up presentation. So this is the typical cost price of PV systems, and it's the cost price of the non-modular costs. So that's inverters, the racking, the installation, the labor costs, that is included in these costs. So what you see now is that the modules are even not the most expensive component of a PV system anymore. It's all the other stuff which is more expensive. And here you can see even the large-scale utility. If you put, for instance, onshore and offshore wind, here you see solar PV. You see that this is the typical range where electricity is generated with fossil fuels. So onshore wind and solar, they already undercut the cost prices of making electricity using, for instance, coal, and certainly using gas or using nuclear energy. So in terms of generation, those renewable technologies are the cheapest technologies around the world available. That's quite interesting. Of course, if you look at the energy infrastructure, it's more than only generation. It's generation, it's distribution, it's storage, and it's the consumption. But in terms of generation, like renewables are becoming very cheap. In that terms, they are becoming a kind of disruptive force in fossil fuel-based energy infrastructure. So now let's move to the PV technologies. And PV technologies, you often have like the very famous chart of NREL. I see I lost it in this presentation, but I usually present the different technologies we have in terms of efficiency, but also in terms of the area. So if you talk about modules as we know them, we are in devices which have an area like this, and here you see the typical conversion efficiencies of modules based on crystalline silicon technology, and this is the dominant technology. 95% of the market and even more is based on these technologies where you have those wafers, so those more cells here, they are connected in series, and then they generate a certain voltage and current, and here you see a typical panel like that. You have different type of technologies, and so the typical efficiencies of modules for this technology are ranging from 70% for the very cheap modules up to 22% for the most expensive one. And SunPower here, this is an example of the niche, the very high efficient panels on the market, not the cheapest one. So this is the dominant technology. Here you make the cell, and from the cell you make basically the module. Then you also have a technology that's based on the 3-5 semiconductor materials. So you have to think about semiconductor materials like gallium arsenide. And with these technology, you can make the world records. These semiconductor materials are the ideal semiconductor materials that have the best properties, and you can make very high efficient solar cells with it. The problem is that making those solar cells is very expensive. So you won't see this technology on residential roofs or in large-scale utility. So you will see them, for instance, in space applications. So sending it to space where yield per area is very important and cost price is not very important. So they are used to supply satellites, or in very niche applications, like in concentrated solar power. So then you use lenses to concentrate the solar light on 1 square millimeter of solar cell. And then you have the thin film technologies. The thin film technologies, for instance, the biggest manufacturer worldwide is First Solar. They make solar cells based on the semiconductor material cadmium telluride. And so it means that you use a very thin layer of material. You have to think in not more than 5 microns, so that's 0.005 millimeters. Here the thickness of the semiconductor material for the crystalline silicon is in the order of 140, 180 microns. So these technologies are a factor 100 thinner in reference to the conventional technologies. So you use less material. It also gives the advantage to develop very next generation PV modules like the flexible module you see over here from Hyatt Solar. And I will come back to this technology. What you see is that the conversion efficiencies are lower than that of crystalline silicon, but you use less materials and you might produce this at much lower cost. But I will come back to that. And then you have the new materials rising at research institutes and universities. And these are based on organic type of semiconductor materials. And for instance, the new kid on the block is now currently perovskites. A lot of research are being done at universities. Both materials still are facing problems because they are not very stable yet. So it means that, for instance, the perovskites, they might be suffering from light, temperature, the material decomposes, but also they are not very chemical stable. So you have to spend a lot of money on encapsulating them, protecting them against moisture, water, because water, that breaks down, chemically breaks down, dissociates these type of materials. So they are only in the research stage, and there are no commercial products on the market, and it's still a challenge to even bring them to the market, in my view. So what I will be focusing on is the thin film here, and certainly the thin film silicon technology. We are working together with the Hyatt Solar company on developing this technology, which in certain metrics will have a lot of advantages. It will give different opportunities to different applications than nowadays the dominant crystalline silicon technology. I'm not saying this is going to replace this technology, but it will allow photovoltaics to be integrated in areas or on facades and roofs which are currently not available or to carry any solar panels. And here you see some examples how this looks like. Here you see, for instance, the integration of a lightweight, flexible solar modules. Here you see that you very nicely can integrate it in very fancy architectural designs and buildings, but also it allows you to have applications which the current technologies cannot supply. So here you see, for instance, the silos which store chemicals or even chemical fuels. And so you cannot directly mount a PV system on this due to safety regulations. And so a fall like this is also allowing to cover, for instance, these enormous surfaces, to also have them generating renewable electricity. So due to the lightweight and the typical temperature characteristics of this technology, it allows to apply it on surfaces like this as well. Next to that, as it's a lightweight technology, it also means that in areas where you are limited by surface, certainly in the Netherlands, you would like to install your large-scale utility PV farms on water, for instance, like in the Netherlands on the North Sea. But even like for the situation in Indonesia, where you have many, like 1,000 islands, it would be nice if you could generate your electricity just offshore. And using current crystalline silicon technologies, it means that you have to invest a lot in the mechanical floating construction. That makes it quite expensive. If you have a technology which is very lightweight, it means that you can build relatively cheap structures on which your PV panels are floating and supplying your electricity, and without sacrificing land area, which you need to use for instance, food production as well, for agriculture purposes. And if you look at large-scale utility, here you see, for instance, a visionary plot where you can simply roll out this lightweight, flexible PV technology. So it's easy installation, but also you need much less mechanical components to mount the systems, which is currently a very important part of the cost price of the technology. So it's a new technology which allows you for the entire system to go to lower cost. And of course, if you have a flexible module technology, it also allows you to have very nice integrations in grooves and facades. And here you see an example how custom made that, people without any knowledge about photovoltaics, they see a roof, but they don't even realize that a solar panel is on these roofs. So you have a variety of applications. But even thinking about in the Netherlands, for instance, we have many industrial buildings with flat roofs in which the construction is built just to hold, for instance, in the extreme situation, 30 centimeters of snow. But the roofs cannot carry the current glass encapsulated technologies, but they can carry a lightweight product. So you have certain roof constructions which you can cover with such lightweight, flexible product as well. So the space of application is increasing. The Hyatt Solar is developing this, and also it has an agreement with industry in Indonesia to build one of their manufacturing plants in Indonesia. Because as I showed you, this technology will have also unique properties which will benefit electrifying neighborhoods and areas, but even rural areas, like for the last mile electrification challenges. So this PV technology is very helpful. And so Hyatt Solar is going to build a manufacturing plant in Indonesia, also to supply the local markets there using the local supply chains. So talking about the thin film silicon technology. I'm now going to have a short academic part in my presentation where I'm going to talk about the principle of this photovoltaic technology. So it is based on different phases of the silicon material. And here you see, for instance, a very chaotic lattice building up. And this is what we call an amorphous lattice. And silicon materials which are structured like this, we call amorphous silicon. And this is how on atomistic level crystalline silicon looks like, and this is how amorphous silicon looks like. And so in this technology, we use, one of the phases, we use this type of material. And we're using something which is a mixture between crystalline silicon and amorphous silicon. And that is shown in the next plot. So
sorry, Prof. Arno, your time is about another 10 minutes.
Another 10 minutes. Okay, thank you.
Yeah, sorry.
Don't worry. So
because we have a question and answer session.
Okay. So then I will speed up a little bit here. So so we have these different phases, and so if you talk about solar energy, you're talking about light absorption, creating charge carriers in the semiconductor material, and collecting that. And it means that you have to transport your charge carriers, and you have basically two mechanisms to do that. It's diffusion, where it's based on density differences, but you can also apply an electric field on a solar cell. So there you can move the charge carriers. And the interesting thing is of the technology of the thin film silicon is that we use the trick of the electric field, and that's being done by making the absorber material, and then, as we call it, doped materials at the front side and at the back side. And with this trick, you can create an electric field within the semiconductor materials, which you show here, such that you can absorb the charge carriers. And we call that a PIN junction, and that's on which the thin film silicon technology is based. So, sorry, I'm being disturbed by another program. So here you see the materials which are being used for these technologies, and what you see is that these technologies are heavily dependent on the four valence materials here, like silicon, germanium in combination with oxygen, carbon, and hydrogen is being used. So these are all the typical materials used over here. And the interesting thing is of using different materials is that they also absorb different parts of the solar spectrum. And that you can use in very smart ways in as we call it, multi-junction solar cells. If you look at the solar spectrum, consists about discrete packages of energy. We call them photons. And we have in the blue part of the spectrum, those photons have a lot of energy, and in the red part of the spectrum, they have not that much energy. And so basically what you see over here is the absorption of the photons and how the energy is exciting electrons from the valence to the conduction band, creating free charge carriers. But what you see is that in this mechanism, a part of the energy in the light is basically not really being used. You only have to cross the threshold energy that of the band gap. So using more type of materials in what we call multi-junctions means that you can more efficiently use the energy in the spectrum. So you can generate higher voltages at the same current, which you have less excess energy which you don't use. And this is basically how the solar cell looks like. You have a top cell absorbing the blue, the greenish light, and the bottom cell absorbing the red and infrared light of the solar spectrum. And this is the typical structure of the solar cell, how it looks like. And this is also the typical structure as Hyatt Solar is generating that in modules. And here you see how different cells are absorbing the spectrum. If you now look at, this is the crystalline silicon modules as we know it, and this is the typical modules for thin film silicon. If you look very carefully, and I don't know whether the resolution is high enough to show that, but here you have stripes of solar cells, and that is one solar cell. So one stripe over here is the same as here, one square wafer-shaped solar cell. And so making these solar cells, basically you are depositing that on a glass substrate. And here you see that we are using lasers to define these solar cells, to make those stripes. And this is called laser scribing. And then you get structures like this in which you have here the solar cell and you have the current going through the solar cell, and the current is then connected with the next solar cell. So this is interconnection. And this is different than from the crystalline silicon technologies. There you have just cells where you connect them with aluminum bars or metal bars. Here you do that with laser scribing, and then with smart tricks you connect the front side of the previous cell with the back side of the next cell. So then you can connect them in series. If you look at the thin film technology, it has been developed by many companies, university, research institutes worldwide. So it's a very mature technology. And here you see that there are a lot of industrial production lines being developed, how to deposit this technology on glass. Hyatt Solar is unique because there they deposit not the solar cell on glass, but on a temporary aluminium foil, just the aluminium kitchen foil. And on that, they deposit first the entire structure of the solar cell. So the metal oxide layers, the semiconductor silicon layers, the metal back contacts, and then they do the laser scribing, making the structure, design the solar cells, then add a carrier foil to that, then remove the aluminium foil at the front side, and then connect there the encapsulant, and then you have the flexible. So they use the substrate, aluminium foil, as a temporary substrate to end up with a flexible product like you see over here.
Your time is, sorry, Prof. Arno, you have another 3 minutes.
3 minutes, yes.
Yes,
so,
sorry.
So what are the advantages of this technology? The advantage of this technology is that, of course, in a roll-to-roll process, you can make very large modules. And also quite interesting is that here you see again the drop in the cost price. This is crystalline silicon. This is thin film glass. And here you can see with flexible, you can arrive at very low cost prices. And another very important thing is that silicon, it's very resistant against water. If you want to make it from other thin film semiconductor materials like CIGS or cadmium telluride, you need to protect it against water. So you need very expensive encapsulation materials. For silicon, you don't have this problem because here, this is a demonstration, for instance, how I made out of silicon material an electrolyzer device to convert water. So this is hanging in water for 30 days with no reliability issues, demonstrating that silicon is very reliable against water. And here you see that you can make it very, very, very cheap and reliable. And the source materials being used, if you compare it, for instance, to other materials. So here, there's the abundancy of materials worldwide. And here, cadmium telluride, this technology is dependent on materials like tellurium, which is not abundantly available. What you like to have is technologies which depend on elements in the first, in the periodic system, the third elements which we have in the periodic system. So, for instance, CIGS also has some issues. The new technology perovskites has some seriously issues in terms of abundant materials. Thin film silicon you can make it, manufacture it from the abundantly available materials, similar like the crystalline silicon. And the advantage is here you see the wafer thickness, and here you see at this the silicon utilization, so the amount of grams mass used per watt peak of generation. And you see that crystalline silicon has gone through an enormous evolution, advantage that less and less materials are being used to produce the power. Here you see that thin film silicon technologies can do this in terms of material utilizations a factor 100 more efficient. So you use 100 times less silicon material for the same power being produced. And this is certainly becoming important if we have to think about silicon supply chains, if we need 70% of our energy generated by solar electricity in the future. And this allows us also to have those very fancy technologies here, like you see applied, where we can have a very cheap balance of systems. And here you see, for instance, a comparisons of crystalline silicon. What is the total cost of the system? So here the blue is the cost of the modules. Orange is the balance of system, the mechanical parts, for instance. And if you have an 18% module product of crystalline silicon, you arrive at these cost prices. If you use a thin film silicon, for instance, for a fixed rooftop or for a floating application, you can save a lot of money in the balance of systems over here in the mechanical parts, making the normalized price of this new technology much cheaper. And so sorry. There I would like to conclude here.
Okay, so, sorry. We have a lot of questions already waiting.
So this shows like the advantages of this thin film technology for the future. So the conclusion is that a new technology gives new opportunities how to use the PV technology in the integration of small systems up to large systems. So thank you. Are there any questions?
Thank you, Prof. Arno. It's very interesting. I would like to give you another an hour or 2 hours for you, but because we have another speaker, keynote speaker, Pak Latif Gao, waiting for us. So we already have 6 questions. For more attractive discussion, I would like to ask Mr. Mairiza from UTM Malaysia. If you want to ask directly, please unmute yourself and ask directly through Prof. Arno. Okay. Do you still hear? Or maybe I would like to go to the next question from Este Nugroho from Poltek CWE. Are you still there? Please unmute yourself and ask directly to Prof. Arno.
Okay, thank you very much, Ms. Dedelia Jarianti. With me, Este Nugroho from Polytechnic Kelapa Sawit, Citra Widya Education, from Java, Bekasi. Thank you very much for the good presentation, Mr. Arno Smith. I want to ask to you, why energy PV very significant for plant energy? Why?
So sorry, there was a hiccup in the audio. Could you repeat the question one more time?
Oh, okay, thank you. I want to ask, why energy PV very significant for plant power energy in work?
So why the energy?
Yes, why energy PV?
Maybe solar energy.
Yes,
maybe
yes.
solar energy very significant in
Power plant in the
generate power.
yes.
So why solar energy is very important? Why it will become important, and not other technologies?
Yeah, that's a question actually.
That's the
Okay,
question.
yeah. So yeah, if you look at, if you would like to generate energy and in renewable ways, we have a few options left. So you have hydroelectricity, hydroelectricity dams. If you look worldwide, the spots, the locations which are suitable for that are basically being used. Maybe in Africa, there are still some locations where you could utilize hydroelectricity, but we cannot increase, or we cannot triple the hydroelectricity capacity quite easily. So the solutions left are basically, you have to look at ocean technologies, wind energy, or solar energy. And even if you then look at the yield per area, for instance, if you have to place a large-scale utility wind farms and compare that with solar electricity, solar farms, the yield per area for solar farms is higher than that of wind. Of course, the challenge is that during night there is no sun and there is no generation. So for solar electricity, daily storage is more important than for wind. Like in the Netherlands, we will have a combination of wind and solar, because we also have huge seasonal fluctuations in solar electricity. But if I look at the solar belt, so the large region around the equator, solar electricity is the solution. It's the cheapest solution. It's in terms of yield per area. It's the best solution, and also in terms of energy return. So the energy payback time and stuff like that. Supplying a circular economy in recycling these materials. Solar energy will make the most sense. I'm not saying that wind energy and hydroelectricity are bad. We also need them very much. but for the largest contribution, solar electricity as a technology has the biggest advantages to integrate worldwide.
Okay, thank you very much for your answer, Prof. Arno. We have another question here from Bu Petiana Indri. Please unmute yourself and ask the question directly. Please, Bu Peti.
Okay, thank you very much.
Excuse me for a moment, Prof. Arno, could you please turn off the sharing so we can see all the audience?
Yes.
Sorry. Okay, Bu Peti, please.
Okay, thank you, Ms. Dede. Thank you so much. My honors, Mr. Dean, Pak Budi, terima kasih. Okay, hello, Professor Arno. I'm Betty. I'm head of Entrepreneurship and Career Development Center in University of Pancasila. And how many days ago, I invited Mr. Latif as a resource person in a research collaboration webinar about research collaboration as an alternative to the transition internship before entering to the world of work. Then I hope Professor Arno can be our sources next in collaborative research for students and lecturers at University of Pancasila. Could you, Professor?
So
okay. Okay, thank you. So my question is, this is Arno for me, can be asked directly for you. So Mr. Arno, in Indonesia itself, we have encountered many models of solar energy, but I believe this is very different, of course. So how do you predict about Southeast Asia for the use of solar energy related to existing climate unpredictable now. Can it be used for another energy saving, and whether it can be placed in housing for a small quantity? It can be used to produce a maximum to the housing, because it is this is very expensive to investment, of course. Thank you. That is my question.
Indeed, so if you look at residential PV, is it useful and can be applied there? Yes. If you look at the financial aspects, you have to, of course, compare it to the local energy and electricity market. So basically, the system has to compete with the electricity supplied by the grid when there is a grid available. In that sense, like in the Netherlands, electricity is very expensive. In the Netherlands, as example, and even the Netherlands is one of the darkest places in the world in terms of solar radiance. So there, the current systems, you earn it back within 7 years. That's in the Netherlands. Having, for instance, an electricity market which is heavily subsidized, or where electricity prices are very low, and there it might take a longer time. But of course, if those low electricity prices are based on energy generation using fossil fuels, it means that you also are subsidizing CO2 emission technologies. So if you look at the whole value chain, having a PV system residential will be cheaper. Whether in the current market for the consumers it's cheaper, and I don't know exactly how the market, the electricity market, how it's arranged in Indonesia. It might be that electricity supplied could be still cheaper, and maybe the low price could hinder a fast payback time of your system. But if you don't have any access to electricity, and certainly if you're looking like at islands where it's very hard, where you depend on the diesel generators, PV is a relatively cheap solution to the problem, so even there, whether it's an autonomous system or it's a grid connected system, it's getting so cheap, and the benefits of having no CO2 emissions will make, if you would calculate fairly the entire costs related to it, it will be cheap. But of course, it also depends on how the energy market is arranged. So, and if you could then go to large-scale utility applications, there I showed the graphs where, it's a very cheap generation of electricity. But then the question is, how are you using that? Do you have to store a part of this? And then you have to invest in the infrastructure, further in the energy supply chain, where the storage of electricity will become a challenge. And how cheaper the solar electricity will be, the more room you have to invest in the storage technologies, even to compete in current energy markets. Did that answer your question?
Okay. Bu Peti. Okay, thank you very much, Prof. Arno. There is another about seven question, but due to the time limitation, so maybe only 3 answer will be asked directly to Prof. Arno. Meanwhile, the rest will be answered maybe by email, if you don't mind, Prof. Arno. There is another question. Maybe I would like to give the time for Mr. Ahmad Ridwan from Universitas Andalas, Padang. Are you still there, Mr. Ahmad Ridwan? Okay, maybe we go to the next question.
So Ahmad, I see here in the chat he has an
Yes.
interesting question. So it's about that materials on the market that are adapted to the European and countries.
American countries, yes, that's it.
So yeah, in terms of reliability, it's very interesting that you should design the modules to the local climate, because there are subtle differences in climate and also in spectrum, total irradiance, the typical temperatures the modules are on. And what you see is that you have to subtly tune the design of the modules for instance, a tropical climate in reference to, for instance, a colder climate in Europe or in America. So, also in our lab and with our partners, we're looking into that. So we exposing or test modules to different type of climates. Yeah.
Okay, that's the answer. Thank you, Prof. Arno. How about Dennis? Dennis Andre here has a question. She is a student from Universitas Pancasila. Is Dennis here? Maybe you can ask directly to Prof. Arno. Please unmute yourself. Or okay, there's Dennis.
So.
Hello.
Yes, Dennis.
First thing first, thank you for the inspiring presentation, Prof. Arno. My name is Audrey from Pancasila University. I want to ask you some questions. First question is, what is usually the problem when using solar power technology? Second question is, what are the factors that determine?
First question.
Yes.
The problem with PV technology, yeah, it's like if you look on PV system level, in operation, it's sometimes that you have to install it smartly. You might have shading issues like growing trees, which shade partly the system. So it's in installation. Sometimes you have to know what you're doing. On the bigger picture, integrated in the energy infrastructure is, of course, the daily fluctuations in the generation. So in the big energy transition, you also need some smart storage technologies accompanied with that. But Latif Gau will also go into that in the later in the second presentation.
Next question, Dennis. Would you like to ask the next question?
Yes. What are the factors that determine the selection of material for design?
So selection of materials of the design, it means that supply chain abundantly available.
Yes.
Secondly, you also don't like to use toxic materials because they will be distributed and installed everywhere. And it's also very important that after the lifetime, we recycle this material again. So you don't want to have toxic materials disposed. Of course, cost price wise, but yeah, the more abundant materials, the cheaper they are usually get. And also important is, can it supply a technology which you can have power per mass of material being used. So if you can use it in thin film, like if you think about tens of terawatt scales in the future of solar power, you want to use as less as possible material, but it also means the material should be reliable in its operation, and also like resistance against weather conditions against the water. And all these aspects determine which material will be the smartest solution. And looking at this, I think that silicon, whether it is wafer-based or thin silicon, will the coming decade certainly play a very important role as PV material.
Okay, thank you for Prof. Arno for your question. Our time is now 3:44 and another 1 minute 3:45 here in Jakarta. And I would like to give appreciation for Prof. Arno for presentation and answering all the questions, although there are some questions cannot be answered because it's time for Pak Latif go. I'm sorry you keep on waiting, Pak Latif. Sorry. So before to Pak Latif go, please give a round of applause for Prof. Arno. Okay.
Thank you very much.
Prof. Arno. And now we go to our, pardon me, Prof. Arno?
Thank you very much and thanks for the questions.
Oh, you're welcome. You have another 2 questions to answer. Okay, sorry. Now we move to Pak Latif Gao. And please give your presentation about 45 minutes. So we will have enough time for question and answer because the response of our attendance is so wow unpredictable. So now we give a time for question and answer longer time. Okay, Pak Latif. I hope you can manage that.
Oh, for sure. So I can manage. Actually, I can do a shorter, but anyway. Very nice presentation from Professor Arno. If you talk about PV technology, especially in the thin film, Professor Arno is the guru. So actually, you guys have a very good opportunity to ask any question about this technology. And Professor Arno also mentioned that we are going to set a factory in Indonesia together with Pertamina, which will be realized in the coming 2 years at least. Anyway, thank you very much for the time. You stay, Arno, here because I think it's nice if you can still have some time to follow our seminar. And it may have some more questions.
I will stay online, but I also in parallel in another meeting.
Okay. I just don't know how to make what is this spot? Oh, this is it. Okay. So again, thank you very much. Selamat, what is this? Selamat sore for everybody. Selamat sore, Pak Dekan or whatever from the University of Pancasila, my alma mater, Prof. Arno. So I'm very happy to be part of this seminar. Professor Arno is, of course, is a guru on this technology, and I am just a practitioner. I am just a businessman who try to implement the technology which is produced by the professor. So here I am. I try to present the concrete project from one of my company. Battery. So one of the question was, what is actually the weak point of this technology? I mean the solar cell. Basically, the main critical part is battery, is the storage system. We know that the solar cell is based on the sun, and the sun is only during the day. And if you talk about the Europe, and now it's only a few hours per day, 3-4 hours per day sunlight. That's one. Second is that, of course, you have cloud, rain, so that you don't have that absorption. You don't have the radiation from the sun. So the best thing is to store the energy is with the battery. So I'm going to present a little bit about the technology itself, which is not lithium battery. We call it a crystal battery because it's made by organic salt, garam organic. We make it crystal for the electrolyte. That's why it's very safe and not toxic. It's very green and then it's easy to be transported without any harm, hazardous material on it. Here in the picture, you see one of the model that we set up, and the project is ongoing. I started this project already 2 years ago with Ministry of Desa, which my local company in Indonesia for this project is Baterai Asia Tenggara. We present this to the Ministry of Desa, Bappenas, and ESDM. And we like to actually have one pilot project to show that our technology are proven with our own cost. But I will show you my, this is the project that we are now ongoing. We have a survey for this island. This is the Pulau Tunda Island. It is located only 2 hours from Serang. So this is Banten. Actually, you know Pulau Seribu. Pulau Seribu is in DKI, the Thousand Islands in Jakarta, and Pulau Tunda is in the part of West Java, Banten. And it's 2 hours by boat from Serang to this island. And they have only 3 hours electricity for 320 homes, 320 house. They only have 3-point light at home. It's 3 hours per day. And every household pays per day 5,000 rupiah. Yeah, so the cost per watt hour is about 65. We calculate that basically they need a minimum standard about 4,000 watt hours per day, which is total for the whole island will be 1.2 megawatt. So the system capacity will be about 1.3 kilowatt. So this is the, how you call it down, page down, okay. Now this is our design, what we propose to the island, where we calculate the need of the electricity per household. We calculate 400 watt. That means in Indonesia is R1, 450 volt amperes. And the total is about 3.6 kilowatt hours. So if you made 4,000 kilowatt hours per day, they will have reserve. So we have a LED light, electric fan, refrigerator, LED TV, phone chargers, and some additional for music. So you can see here where we come up. So currently they have only 3 hours electricity per day. We will go to 24 hours, 247. They have only 25 watt peak per day, and we go for 400. So 3 hours times 25 is only 75 watt hours. And we are going to make 4,000 watt hours per day. You can see here the difference in cost. This is per watt. So this is significant reduce on cost. We supply the technology, including the battery. That's why we can go up into 24 hours, yeah, 24/7. How we do this? This is our technology then. We show you a little bit. So the power generation is still based on thin film. No, PV. In this case, we still use crystalline PV because our factory for thin film is not available yet. This is our system, a storage system. We have communication information, a battery management system inside. We can also connect it to the internet Wi-Fi, so we can control from a distance with a mobile phone or in the monitor, and we can distribute it to home. And we can also switch off a specific home if it is necessary. For instance, if they don't pay or there's nobody home, we can switch it from a distance, from remotely. So, the system is look like this. We can have a solar input to the charger to the storage. We can even have a genset if it's necessary, but in this case we don't need it. We can also charge the battery with a windmill or even from on grid, and we can also light up the telco tower if necessary. Yeah, I show you the equipment details. So the system of PV system used to load the system, we have 250 kilowatt peak, 250 kilowatt hour generation per day for that solar panel. We have a load and charging the battery. We have 100% daily capacity. This is about 1,400 square meter needed, yeah, area, I mean land. If you use a thin film, it will be different, but this is still a standard crystalline technology. In total, 950 panels. About so if we have a floating panels, that will be much cheaper, of course. But for 1 megawatt hour per day, we need about 1,400 square meter land. The system inside, we have a storage system. We store with a battery, with a solid lead crystal battery. I'm going to explain a little bit on this later. We have a 2 megawatt hour. We have 3-phase. We have 250 kilowatt inverter. Dynamic string management. This is actually charging the battery with intelligent charging battery system, where we have what we call BMS, battery management system. And inside the cabinet, inside the container, we have also an artificial intelligence management system, which can predict algorithm and online weather forecasting for an optimal application. This technology actually used by NASA to predict the radiation and sunlight, how many hours per day, and when will be raining, and what's the autonomy that is possible. It's all inside the system. Inside the system, we also have all the communication we can control. This is actually the system we put in the package. So we have power monitoring system and fire monitoring, site security, and other applications. So we can all monitor the performance of the system from a distance by using a remote and Wi-Fi. We can check the tank, genset, temperature, smoke fires, remote, all these things are inside. So what is the main key is the battery. Again, the critical thing is the battery for the energy storage. Our storage system, we call it crystal battery. Yeah, this is unique technology, really to overcome the conventional battery problems by having all solid state electrode. Yeah, that allow us to charge and discharge deeper, means we can have a DOD until 100%, 100% DOD discharge, and we can use it as often as we want and can have very long life until 15 years or even more. And we are going to prove this in the island to show the government, to show the user that we are convinced with our product. What is actually different? Why is this technology so different? Actually, it's made by inorganic salt. Yeah, so it's really organic material inside. It's organic substrate. So that's why optimizing the reaction between the electrolyte and active electrode material. Reaction also improve the product safety, making it less harmful to installers. So it's no toxic at all because it's organic material. You can check it on the website. It's all organic. It's very safe for the environment. That's why we call it a green rhino. To have a little bit insight about the product itself, I want to show you a short video about the test program, how we test this battery in a very harm way. So it is, let me show you the video. Hang on. This is the test process which we done for this battery. This is the ignition test. We try to ignite with a very hot plate and let's see what happens. Hot plate, 300 degrees. No force ignition. Toxicity test, yeah. Fire test, yeah. If the building is having fire, there's no explosion. You compare with if you compare with lithium ion, it will burn the building. Function test, yeah. Yep, still operating, still good, still function. Drop test. It's a drop first time, first attempt. Nothing will happen. Second time, second attempt. Then you can see it damaged, but still function. Overcharge. Yeah. Okay, so that's about the test, and I want to show you the comparison basically on all battery technology which is available nowadays. You have the lead acid, we call it a wet battery, battery basah. This is standard one for our cars or whatever, and we have a gel battery, AGM, which is actually, we call it in Indonesia battery kering. And we have our crystal battery, we have lithium ion, I have nickel cadmium. So you can see here the chart, temperature can go up to 65 degrees. Same also with the nickel and lithium. And as you might know, if you guys understand about the battery, if the temperature increases 1%, the performance of the battery will decrease about 10%. But ours doesn't matter. Yeah, so the capacity, that's why, especially in Indonesia where the high temperature, then the lifetime of the battery is very short, can go only for 2 or 3 years. Yeah, this is basically what they put here is basically at 25 degrees, and for us it's based on that one. Yeah, transport, this battery, this is very dangerous because they have toxic and you cannot carry it in the airplane. Lithium ion you cannot carry also in the airplane because it can explode, nickel as well, so it cannot be transported via airplane. Our battery, there is no toxic, no explosion, so you can carry the airplane, no problem, because it will not explode. It's crystal, it's actually a stone. Handling safety is very good. Fire risk, no fire. You see the test already. Performance is very good. So basically, if you go down into the price, because that's also very important parameters. If you take lead acid as a standard price, let's say $1, then gel, the dry battery kering is about 20% higher than lead acid. Our price will be 2 times higher than the lead acid. Yes, but it's 5 times higher for lithium ion compared to the lead acid. Means our price compared to lithium ion is less than a half. Nickel is 4 times. So if you talk about the total cost of ownership compared to the lifetime toxicity, transport, storage, and everything, we come up with that this battery is the best in a total cost of ownership. So if you see the key features, the long lifetime can go up to 18 years, because if you see the cycle curve, 25 degrees, 12 volts, you can have a number of cycles. If you have only DOD, depth of discharge, to only 10%, it's really can go up to 18 years, 20 years. Deep discharge capability, you can charge from 100 into 0 and it will go back again. It's not same with the lithium ion. I mean, if you compare with the one that you in our mobile phone, in 1 year time, the degradation is even more than 10%. So it's normal when we buy a new phone, we can charge it for 1 day, one times, and we can use it for 1 day, even 2 days. But 1 year later, we have to charge it every day. Yeah, but with the lithium, with the crystal, it's not necessary because the degradation is only 1% per year. So these are the features. So we can have a fast charging. If you understand about this, it will be 0.3 C charging system, means we can charge it very quick. It can go extreme temperature, yeah, until 40 to minus 40 to plus 65. The safest, no thermal runaway, no gassing, no leakage, no spontaneous ignition, will not burn. Long life, if we store this battery 2 years in the storage, the capacity will still be there and will not degrade in 2 years time if you store it in the storage. Because it's green, because it's from organic material, can be recycled up to 99%. Of course, nothing can be recycled 100% because you have always waste, but this is a green, so no toxic, and it's very environment friendly. And the crystal technology, again, because it's from the organic, inorganic salt, it's very unique crystal, and the plate is also powerful usage. Yeah, this is actually can speed. The transport is very easy. Extreme temperature quality is guaranteed. The pricing, I mentioned it. This is just our calculation for the investment which we are going to do in the Tunda Island. We are going to do this for the pilot. We pay this for government. On the other hand, we like the government to guarantee us that if we prove this, we like to have agreement that we can implement it in, let's say, all remote islands. So here we said we have a price of 14 cents per megawatt hour. But this calculation is very, still lot of reserve, lot of buffer. Now our calculation, this calculation was made in 2018. By the time we calculate better, then we actually came up into 12 cents per megawatt hour, even less nowadays. So again, solution for the remote island, once we have the thin film technology, it will be best match with this, because then we can have a floating application on the island, especially where you don't have many space available in the ground, then you can have the sea, and then we can have very cheap and reliable application. I think that's Ibu. Again, go back to this the calculation that we have, but I think that's my presentation, just to give the hint about what the application on this technology with using the right storage technology. Terima kasih, Bu.
Okay, thank you, Pak Latif Go. Maybe if the attendants have a question, would
Yes.
you like to ask directly, maybe by raise hand in Zoom chat? Okay, maybe I would like first ask to Pak Latif.
Yeah.
What is the it seems that the battery is so good.
Yeah.
Compared to others, but I think as another product, there must be a limitation of this product. Can you explain what it is?
Okay, yes, it's good. It's no technology can do everything. Yeah.
Yes.
The disadvantage of this is the weight is heavy, so you cannot use this for electric vehicle. Yeah, this is better for storage, energy storage. You can use it for the forklift or the buggy, because it's okay. The weight is not matter. Even for we use it in America and in the Netherlands for the fire pemadam kebakaran, firefighters, because during the spraying of water, the engine of the car should be shut off, so they need a lot of power, and they use this battery. They carry this battery in the firefighter car. This is quite heavy. So for the stationary energy storage, especially for this application, is the best solution, and also the cheapest one. but not for the electric vehicle, because it's too heavy. Then you have to use another technology like lithium ion or others. Yeah, that's why very specifically propose this for the Desa electrification program, which is now taken by the Minister of Energy as a pilot, and we are going to roll out to 1,000 islands, because PLN officially announced that they have 2.6 gigawatt diesel gensets still in operation throughout the island, and it's cost them average 30 cents per kilowatt hours, while our solution, and we guarantee that, is from 11 to 15 cents per kilowatt hours. And we also finance the project. Yeah, so government don't need to invest in capex. We will finance this from the Netherlands, and we will operate as well, and the price is much cheaper.
So that's the bureaucracy problem with this project. Yeah.
Yeah.
Anyway. Okay. So as the Prof. Arno mentioned before, that in 2050, the PV technology will be around 69% of the power generation. So with this implementation of your battery, is it possible to do it, to implement it?
I already have quite a big project in Indonesia with Telecom. Also some PV project for 100 megawatt. Of course, off grid. If it is on grid, then they can use PLN transmission line supplied to the grid, but only during the day. But during the night, yeah, they cannot have anything if they don't have storage. So to have it completely off grid, one has to have the storage system to be able to supply the electricity during the night.
Okay.
So we don't have any problem. I think I mentioned already that I'm going to set a factory here next year. So first, I don't know, this is the thin film one. Can you?
Okay.
This is the thin film, the solar cell. Maybe let me switch off this. Okay. I don't know if you put it. This is the thin film solar cell. We are going to set a factory in Indonesia for 300 megawatt. I think you saw the picture when we signed the agreement with PLN, with PLN and Pertamina last time. I was also in the picture with the background of the king of the Netherlands. That was March this year, before the COVID. So we signed the agreement with Pertamina and LAN to set a factory in Indonesia for 300 megawatt capacity of this thin film solar cell. It's very lightweight, very cheap, and local content, as Professor Arno mentioned, is all abandoned material. It's all available in Indonesia, the chemical, the gases, the aluminum foil. 96% of the material for this thin film solar cell is available in Indonesia, and it's cheap gases, cheap polymer. It's actually, according to Pertamina, is the waste material of Pertamina. So that's why they agreed to set a factory here. And of course, on the other hand, you have to have a technology for storage. So we are going to build a factory for the solar panel, thin film solar cell. It will be production in 2022, so 2 years from now. Unfortunately, COVID a little bit problematic for us to start. And next year, I will start the factory for the Green Rhino battery. I will start production, a factory in Indonesia for the Green Rhino. Also, the local content is about 80%.
I see. It's a nice technology. So you can combine the thin film with the tidal.
As a battery, yes.
Yes, with the battery, and also with maybe hydropower, or maybe with white.
No, I'm not going to hydropower.
Okay,
I have a tidal. I have seaweed. So I have 4 companies already set up in Indonesia, all renewable energy, but not harming the environment. because for hydropower, we are really bit reluctant to go into the hydro, because then you can harm in some extent to the environment. You have to block some area, those kind of things. But
I see.
for thin film, for tidal currents, or even for the wind, but especially on the battery, I set up already companies in Indonesia for this, and we have already quite some project ongoing.
Wow, it's a great appreciation for you because you are concerned about the environment. Wow, nice.
Yeah.
That's very nice of you. We have to make you a model for this green technology and implement it in Indonesia. And I hope that the government will see it and then agree to implement this technology to Indonesia, because as you see that there is still a remote area untouchable by the PLN, by the power company in Indonesia.
Yep.
Okay, so is there any question? We have still about 15 minutes more to go. There's a question from Pak Ahmad Dovir, but he a question in Indonesia in Bahasa.
You can ask Bahasa or Belanda or English or Java.
Okay.
Doesn't matter. I'm from Sulawesi, but doesn't matter. I can understand Java as well.
Okay, so maybe I will read the question, Pak Latif, or maybe Pak Dovir will answer. Will ask yourself, Pak Ahmad Dovir.
Oke, terima kasih. Mungkin agak gelap-gelapan, mohon maaf nih.
Bahasa Jawa, Pak Dovir.
Oh, oke, bahasa Jawa, mohon maaf. Gini, Pak Latif.
Yes, sir.
Menarik sekali ya baterai kristal itu. Tapi gini, ini kan problem kita kan khususnya adalah terkait dengan harga ya, Pak Latif.
Ya.
Harga pasaran, apakah baterai kristal ini sudah familiar atau memang didesain khusus untuk daerah pedesaan atau memang untuk membantu masyarakat yang energi listriknya tidak ada. Itu yang kita pertama itu, jadi apakah harganya memang murah atau memang baru kita launching atau sudah familiar di lapangan. Karena selama ini kan kita kenal baterai itu kan baterai untuk aki, untuk BTS ya. Itu gimana kira-kira kalau di dalam kota bisa nggak dipakai itu? Apakah nanti bersaing dengan PLN? Nah, ini yang perlu dijawab. Minta tolong. Terima kasih, Pak.
Okay.
Latif, kira-kira seperti itu.
Silakan, Pak Latif.
Okay, I think I explained already. It's all about cost, Pak. Energy is all about cost. I show you the comparison between the diesel one, Rp67 banding Rp2. Yeah, it's all about. I don't know if you follow my presentation. It's all about cost. Yeah. So again, kalau pakai lead acid batu aki dipakai setahun rusak, di overcharge kembung, pasti kembung. Atau kalau enggak leak, bocor. So dia nggak bisa nyimpan energi lagi. Makanya semua proyek-proyek PLN, ISDM, segala macam dipasang di pulau-pulau, pesta-pesta, di pembukaannya potong sapi, potong kambing, 6 bulan mati. Masalahnya di mana? Baterai. Makanya saya tantangin, Pak, saya kasih contoh one island, saya bayar 1,5 juta, I will finance. Ayo kita buktikan, kita sepakat, give me the parameters we agree. Give me 6 months. Tapi sebelum saya pasang, ayo agree. Kalau nanti benar sesuai dengan parameternya, give me the project, 1,000 island. Jangan 1,000 deh, 200 island aja, 200 megawatt. I will finance, nggak usah keluar uang. Saya finance dari Belanda. Kita finance di sana murah kok, bunganya 0,8%, 100%. Ya. But you know, our bureaucracy, our mafia di sini banyak, mafia diesel, mafia solar. It's all about cost, but of course many interest party involved. So that's the invisible hands can stop this. While our people need electricity, but our bureaucracy is stopping them to get the electricity. Yeah. On the other hand, if you listen to Pak Yonan last time when I I spoke many times Pak Yonan during his minister. He said, dia bilang, electricity ratio of Indonesia is 98% something, even going to 99% plus. Okay, but he doesn't mention that some island only 1 hour electricity, 2 hours, but he calculate already as electricity ratio. It's not fair. Ya, maybe intentionally dia bilang electricity ratio 99%, tapi dia nggak menyebut bahwa yang 1 jam, yang 2 jam, bahkan di Papua hanya pakai lampu lilin apa itu, lampu LED, itu dia udah bilang electricity ratio sudah menikmati listrik. No, yeah, that's why. But it's nice, it's a revolution really for PLN that they openly announce that they are going to replace the 2.6 gigawatt diesel genset which still operation in many islands. It's really a revolution because normally they protect it as a mafia inside. I know, sorry, I bluntly, because I fight with them, and I'm Indonesian. I'm living in the Netherlands already almost 30 years, but I still have my Indonesian passport because I have. I'm proud of Indonesia. I don't change my passport, but look what happens in my country. That's a problem, big problem. You want to do something, but on the other hand, we are blocked with the bureaucracy. So yeah, a little bit emotional if you talk about this case. So back to your question, Pak Dovir, everything is about the cost. Whatever technology you propose, if the cost is much higher, then forget it. We can compete with coal. I'm working now with BTS with Telco. We replace all the battery later, but again, a lot of mafia inside, doesn't matter. Baterainya kembung-kembung, bocor-bocor, BTS-nya rusak karena baterainya hancur, mafianya banyak, saya susah masuk. Tapi saya tawarkan, okay, let me maintain it and let me finance it. Kamu nggak usah beli, sewa aja. Bayar cicil, selesai lunas, ambil. That's still big problem. So give me challenge for the cost. Saya mau di challenge.
Okay, wow, you are really emotional about this.
I've been traveling already 5 years, move up and down from Holland to Indonesia every month. Yeah, every month. Because of COVID, I was stuck almost 5 months in the Netherlands, not coming to Indonesia because of the COVID. But normally, every month up and down from Netherlands to Indonesia.
Okay.
5 years already.
I hope your project about replacing the diesel will come true with this solar energy and your battery.
Yes.
And I think the last question is conclude our webinar series, and I really appreciate for Prof. Arno, who's still here. Hello, Prof. Arno. And Pak Latif Gal for wonderful and so sharing presentation. Thank you very much. And maybe there's a question, but we'll ask you later, maybe by email or.
Maybe Pak Budi want to ask question. Pak Budi.
Oh yeah, Pak Budi. Pak Budi.
You can ask Pak Arno, Professor Arno also. You can ask question.
Yeah. Thank you very much, Pak Latif.
Yes, Pak.
It is very interesting to get the idea. What is the best efficiency of the battery or the solar PV, especially for solar PV efficiency?
Arno, can you answer? I can also, but
yes,
you know much better about the efficiency of the solar panel. I mean, compared to the thin film one.
Sorry, I had to unmute another.
Because you're online on the other side.
Yeah. So the question was on the conversion efficiency of solar PV. It heavily depends on the technologies. If you look at the record conversion efficiency, and that are the 3-5 semiconductor materials and multi-junctions, there you are to 46-47%. These are very expensive, complex designs. Okay. if you go to the crystalline silicon technology, which is now predominantly in the market, so panels, commercial panels are ranging from 17 to 20%. The best are 22%, but then you're also paying additional for these type of panels. If you see for crystalline silicon, the lab, the best which has been achieved by Kanaka, Japanese company, is 26.7%.
Yeah.
So there's still some room to get there. So means there still some advantage in production processes to mimic those very high efficient solar cells into a large scale production lines. So that's still development, R&D, room to improve. And then if you go to the thin film technologies on glass, so the cadmium telluride, the CIGS, cadmium telluride, the best modules are in the order of 18%. CIGS is lower, I guess, which on the market will be around 15, 16%. The thin film we are talking about here, the flexible product, there we are currently at 12% conversion efficiency. That's much lower, but you have to realize that you can, flat surfaces cover it much easier. You can cover the whole area because you can walk over it in reference to the crystalline silicon panels, and they usually are in the tail and stuff like that. So the yield per area is the same or even higher if you smartly integrate that. But that's 12%. So that are the typical ranges of conversion efficiencies, but there's also how do you apply the panels in a smart system and application to arrive at the real yields. And also depends on climates, like the temperature, so that what we call performance ratios. So in tropic climates or in deserts, panels can reach very high temperatures. And the higher the temperature of the panel, usually it's going down the performance. So some technologies are more sensitive for temperature effects than other ones. Like the thin film I showed is not that sensitive for temperature. So the performance drop is lower than, for instance, crystalline silicon, which also will have some advantages depending on which climate you use. And also the response on the typical spectrum of the sun, depending on the areas, that can have performance ratio differences. Or the resilience to shading effects. So thin film, the long stripe of solar cells, it's less sensitive for shading effects in reference to crystalline silicon. So there are a lot of factors in play, but in general, conversion efficiency is defined as standard test conditions, like thin film, 12%, CIGS, 16%, cadmium telluride, 17, 18%, crystalline silicon, 17 to 20%, best products, 22%. And then the very fancy technologies, very expensive, are above that. But that are the typical conversion ranges.
Okay. So there is still a open room for efficiency improvement and depend on the price ratio.
I can add a little bit on that, Pak Budi.
Oh, so yeah, please.
I show you this a comparison. This is our feasibility study together with Pertamina. So if you see here, we compare crystalline in yang glass, 80% efficiency with ours, the thin film is 12%. Generated power, megawatt hour per year, we are double. See, so efficiency here is not really a matter because it's pure about the space, area. You can see here, Pak, area utilization is 4%. This is example, Pak.
Yeah.
You can see here, because it's crystal, you can only cover very limited area because it's glass, it's square.
Yeah.
But for our thin film, we can cover all area. It's plastic. We can cut it, we can bend it, so we can cover all area. Yeah. So that's why the power generation is even double. You see the efficiency is higher, 18%, and our efficiency at this moment in our factory is 12%. We are going to increase our efficiency to 20%, 18, 16, 20% in the coming years. But if you compare only the efficiency compared to the crystalline and the thin film, you can see here the comparison part. So the cost is half.
Okay.
6 cents to 3 cents. And the same of others. For that, I can show you many. This is my pre-feasibility study. We do it with Pertamina. So we cover all the shape of the roof. So if you talk about this efficiency, it's purely about the space. But our can use in any shape of the space. So efficiency is not really relevant here.
Yeah.
Yeah. And if you this one part you can see here is in Malaysia. If you use only crystal, then you can only cover, I don't know, you cannot full like this. You can only cover, I don't know, maybe only 40% of the space here because of the square meters, the rectangular glass, a heavy product from crystalline. But with thin film, you can cover whole space. And it can also be integrated with the panels. I mean the roof panel. You can use it here. You can use it on top of this. So, and the battery, yes. Again, the comparison. I can go back to my presentation if you want. I can show you what's the. Sorry, lihat nggak presentasi? Oh, bentar. Maybe I need to. Maybe I need to check. So that again, Pa, I want to make sure that you understand what my presentation about the efficiency. So I hope that, So this is the comparison, Pa.
Yeah.
So, I don't have the graphic, but basically the degradation, our degradation per year is 1%. Yeah. And the lithium ion is 10 to 17% per year. That's why the life cycle of the lithium ion is very high. You can check with your mobile phone. The first year you can charge it and you can charge it once, and you can use it for 1 day. But in 1 year time, you have to charge it every day can be used only for a few hours because the degradation capacity degradation is very high for the lithium. Yeah, that's why we can guarantee. I also talked this with PLN. I can guarantee for 10 years.
Oh, good.
Yeah, but because of the budget and all those kind of things, I say make it 5 years. For me, easy to get 5 years guarantee.
Thank you. Thank you very much. Pak Latif, Prof. Arno.
Okay, thank you very much. Yes, maybe the last question from Pak Budi, Mr. Dean, close our webinar series and also our discussion. Please give us applause for our keynote speakers. Yeah. Thank you very much for Arno and Pak Latif Gau. And before I give it to Mbak Nining, first of all, I would like to announce about the SEMRESTEK agenda for tomorrow. Jadi besok harus ada registrasi sekitar jam 8.40. Kemudian nanti dibuka oleh paralel sesi ketua SEMRESTEK. Kemudian nanti akan ada paralel session dan ini acara ini sudah dibagikan kepada para peserta. Mohon diperhatikan dengan baik. Okay, I think that's all. Mbak Nining, I'll give you this session back to you.
Okay, thank you, Dr. Dede Lia Zariatin. Before we close this seminar, this webinar, I mean, we will take a photo session first. Could you please turn on your camera, everybody?
Smile, yeah.
And with the biggest smile. And this is Salam Pancasila.
Okay.
Professor Arno, would you mind? This is, only one hand, Professor Arno. This is Salam Pancasila. Okay, Erlanda, take the picture, please. 1, 2, 3.
Erlanda di
Okay, next. It will be maybe 4 or okay.
1, 2, 3. Okay, finish.
Finish. Okay. Thank you very much, Arlanda. And we have
Thank you.
yeah, we have reached our seminar, our time. This is a very interesting topics, especially battery is a very essential because nowadays everything is based on electricity. Everything now with the for online class, for buying material or something, so we need electricity. So Puang Latif Gau, because you are from we are the same. I am from Makassar and you are from Bugis, right?
Yes, sir. Yes, ma'am.
Yes. Okay. So this is a very
beliau.
and
Kan pulama saya, pulama saya, senior saya.
Okay, baik Pak Sunardi, Nake from Jeneponto. Okay, we have reached our webinar. Thank you very much from your attention to the attendees, to Mr. Budi, and to Professor Arno and Puang Latif Gau. Okay, thank you very much. Hope we can meet you again in other occasion, and salam sehat selalu.
Thank you very much.
Thank you very much.
Thank you very much, Prof. Arno, Prof. Damir, Pak Budi, and everybody.
Thank you.
Thank you. Bye-bye.
Bye. Bye, Prof. Arno.